When we talk about speed, we usually assume one simple rule. If something moves faster, it must be using more energy or better technology. That idea works well in everyday life and even in classical physics. But it completely fails when we talk about light. Experiments show that light always travels at the same speed, regardless of how fast the observer is moving. This result was unexpected, and it directly contradicted the assumptions scientists had relied on for centuries. To make sense of this, physics had to abandon some of its most basic ideas, not about light, but about space and time themselves. For most of history, speed was simple. If you're on a train going 100 kilometers an hour and you throw a ball at 20, someone on the ground sees it moving at 120. Easy. Speeds just add up. That's the world of classical physics, the one Isaac Newton laid out for us. It makes total sense because it's what we see every day. Want to go faster? Just add more energy. Hit the gas, fire a bigger rocket. Just add more speed. There was no reason to think there was any ultimate speed limit. With a big enough engine, you should be able to go as fast as you want. This comfortable, common sense view of the universe would rule physics for centuries. But a crisis was brewing in the 19th century, and it all started with a beam of light. In the 1860s, a Scottish physicist named James Clerk Maxwell set out to unify the laws of electricity and magnetism. He came up with 4 beautiful equations describing how these forces work, but his math spat out something weird. It predicted that a ripple in an electromagnetic field, in other words, a light wave, would always travel at a very specific speed, about 300,000 kilometers per second, a value we call c. That was strange enough. But here's the part that broke everyone's brain. Maxwell's equations said the speed of light was a constant, no matter how fast the source or the observer was moving. This created a massive paradox. Think about our train again. This time, instead of a ball, you switch on a flashlight. Newtonian logic says the person on the ground should see that light beam moving at the speed of the train plus the speed of light. But Maxwell's equations said no. The observer on the ground would measure that beam moving at the exact same speed c as the person on the train. This made no sense. How could light have the same speed for someone standing still and someone else blazing by? It's like 2 cars driving toward each other, but both drivers clocking the other car approaching at the exact same speed. Physics was stuck. The reliable, intuitive laws of Newton and the powerful new laws of Maxwell were in direct conflict. One of them had to be wrong. Or maybe both were just part of a bigger picture. It would take a young, unknown patent clerk to show everyone the way out. In 1905, Albert Einstein, working in Bern, Switzerland, published his theory of special relativity. He didn't try to disprove Maxwell. He did the opposite. He started with 2 simple but radical ideas called postulates. First, the laws of physics are the same for everyone in uniform motion. This is the principle of relativity. It just means you can't do an experiment to tell if you're still or moving smoothly. All non-accelerating motion is relative. Second, and this was the giant leap, the speed of light in a vacuum is the same for all observers, no matter how they're moving. Einstein embraced the paradox. He said, yes, the speed of light is absolute, but if that's true, something else has to be flexible. That something else was space and time. He realized that for the speed of light to stay constant for everyone, space and time themselves have to stretch and shrink depending on your motion. To get this, picture yourself on a really long train. A light bulb flashes in the exact middle of your carriage. To you, the light hits the front and back walls at the exact same time. The events are simultaneous. But what about someone on the station platform watching you fly by? They also see the flash. But from their point of view, the back wall of the train is rushing toward the light, while the front wall is rushing away. Since light speed is the same for them, they have to see the light hit the back wall before it hits the front. Let that sink in. Two events that were simultaneous for you happened at different times for someone else. Your now is not their now. This is the relativity of simultaneity, a direct result of Einstein's ideas. It's the first clue that our gut feeling of a single universal clock ticking for everyone is just plain wrong. If now is relative, then time itself must be relative. This leads to one of the most famous effects of special relativity: time dilation. Moving clocks tick slower. The faster you move through space, the slower you move through time. This isn't just a mind bender, it's real. As astronauts on the International Space Station age just a tiny bit slower than we do. GPS satellites, whipping around the Earth at high speed, need constant clock adjustments to account for this. Without those corrections, your GPS would be off by kilometers every single day. And it's not just time. Space is flexible too. Special relativity also predicts length contraction. An object moving at high speed will appear shorter in its direction of motion to someone standing still. The universe literally squishes in the direction you're headed. So, let's recap. To keep the speed of light the same for everyone, reality itself has to warp. Time slows down, and space contracts. It's a beautifully strange trade-off. The universe gives up the absolute nature of space and time that we take for granted, all to protect the absolute, unchanging speed of light. Now we can finally get to why there's a speed limit. It all comes back to another little equation Einstein dropped in 1905. E equals mc squared. This reveals a deep connection between mass and energy. In short, mass is just a very, very concentrated form of energy. This changes everything for acceleration. When you push something, you're giving it kinetic energy to make it go faster. But according to Einstein, that extra energy actually adds to the object's mass. As an object speeds up, its mass, its resistance to being pushed, increases. At normal speeds, this change is so small you'd never notice. But as you get closer to the speed of light, the effect becomes huge. The energy you're pumping in is being converted more and more into mass, not speed. The object gets heavier, making it even harder to accelerate. As you get ridiculously close to the speed of light, the object's mass heads towards infinity. To make something with infinite mass go any faster would take an infinite amount of energy. And since there isn't an infinite amount of energy in the universe, it's physically impossible for anything with mass to ever reach the speed of light. The universe itself says, nope. This speed limit isn't just a rule. It's built into the relationship between space, time, energy, and matter. So, back to the big question. Is the speed limit all about light? Nope. Light only travels at this ultimate speed precisely because it has zero mass. If photons had even a tiny speck of mass, they'd also be forced to travel slower than c. The cosmic speed limit doesn't come from light. Light is just the most obvious thing we see that travels at the limit. The speed of light, c, is better described as the speed of causality. It's the maximum speed at which a cause can produce an effect. It's the top speed for any information traveling through the universe. If you could send a signal faster than light, you could create paradoxes where you would get a reply before you sent the message. The universe enforces this speed limit to keep its own story straight. Think of it like this. A circle has 360 degrees. You can't have a 370-degree circle. It's not a limitation, it's the definition of a circle. Likewise, the speed of light isn't a limit on particles. It's a fundamental property of the four-dimensional space-time we live in. Everything is always moving through space-time at one fixed speed, the speed of light. Something at rest is just using all of its speed budget to travel through the time dimension. When it starts moving through space, it has to borrow some of that budget from time. That's why its time slows down. A massless photon uses its entire budget to move through space, so from its own perspective, it doesn't experience time at all. So the cosmic speed limit has nothing to do with how hard you can push a photon. It's a fundamental rule woven into the geometry of space-time. It's the speed of cause and effect itself, the rate at which reality is allowed to happen. For a photon traveling from a distant galaxy to your eye, the trip takes billions of years from our point of view. But for the photon, in a world where time doesn't pass, its journey across the universe is instantaneous. The very speed limit that defines our existence, creating the flow of past, present, and future, is something a photon never even experiences. And it's the reason our universe is a logical place of cause and effect, not just a chaotic mess of everything happening at once.